Good afternoon, Doctor. We are from Group 17. So today we are going to explain about the gas power cycle that we designed. And the cycle that we chose is the Otto Cycle. And my name is Tawani, and my metric number is 202733.
Good afternoon, Doctor. My name is Jayrad, son of Rajasegar, and my matrix number is 203129.
Good morning, Doctor. My name is Muhammad Muawidza bin Muda Bistari, and my matrix number is 202734. Okay, before we start, this is our table of content. There are 4 main contents. The first is problem statement. The second is solution for air standard assumption and cold air standard assumption. The third one is design of gas power cycle, which is Otto cycle. And the lastly is discussion. This is our problem statement questions. An ideal Otto cycle has a compression ratio of 12. The pressure and temperature of the air is at 150 kilopascal and 47 degrees Celsius at the beginning of the compression process. An amount of heat is transferred to air where Qin is equal to 900 kilojoule per kg during the constant volume heat addition process. Determine the temperature and pressure for each point in the cycle by using both assumptions, which is the air standard assumption and cold air standard assumptions. Include the drawing of PV and TS diagram of the cycle. By using the data gained from the calculation, find the network output, the backwork ratio, and the efficiency of the cycles. After determining the temperature, pressure, network output, backwork ratio, and efficiency of the cycle for both assumptions, compare and discuss the result.
So 10 hours for explaining the problem statement. So now I'm going to explain the calculation part for the air standard assumption, in which K is not equal to 1.4. So from the question, we know that at the stage 1, the pressure is equal to 150 kilopascal and temperature is 47 degrees Celsius. And then we convert this 47 degrees Celsius into Kelvin, which is 320 K. And then the compression ratio R is equal to 12 and the Q is equal to 900 kilojoule and kilogram. Since it's an air standard assumption, we need to obtain the value from the table. So from table 17, we obtain that the VR1 is equal to 528.6 and the U1 is equal to 228.42 kilojoule per kilogram. And then we know that the compression ratio is actually equal to a Vmax above a Vmax over Vmin, in which at V1 over V2. So we obtain a formula in which VR1 over VR2 is equal to 12, and then we obtain that the VR2 is equal to a 44.05. So we use this value, VR2 is equal to 44.05 to make the interpolations, and then we obtain the T2 is equal to 825.28 Kelvin, and the U2 is equal to 612.91 kilojoule per kilogram. Then for the pressure, we need to use the ideal gas equation in which that P2V2 over T2 is equal to P1V1 over T1. And then we obtain that the P2 is equal to a P1 multiplied to a V1 over V2 multiplied to a T2 over T1. And then we know that the V1 over V2 is actually equal to a compression ratio, so we just substitute the value of 12 and we obtain that P2 is equal to 4642.2 kilopascal. And then we know that the Qin is equal to 900 kilojoule per kilogram. And then Qin is also equal to a U3 minus U2. So we obtain this formula in which 900 is equal to a U3 minus U2. And then we substitute the U2 value inside and we obtain that the U3 is equal to 1512.91 kilojoule per kilogram. So we use this U3 is equal to 1512.91 kilojoule per kilogram to make interpolations, and then we obtain that the T3 is equal to 1826.95 K, and then the VR3 is equal to a 3.782. And then you use the same ideal gas equation, P2V2 over T2 is equal to P3V3 over T3. And then from the PV diagram, we know that the V2 is over the V3, so we just cancel it out. And then we obtain that P3 is equal to 6.59 kilopascal. So it means so we obtain the formula of VR4 over VR3 is equal to 12. So the VR4 is basically equal to a 12 multiplied to a VR3. So VR4 is equal to 45.384. So we use this value to make the interpolations, and then we obtain that T4 is equal to 1816.64 Kelvin. and then the U4 is equal to 605.85 kilojoule per kilogram. And then for the same method, we use the ideal gas equations to find the P4, in which that P3V3 over T3 is equal to a P4V4 over T4. And then we obtain that the P4 is equal to a P3 multiplied to a T4 over T3 multiplied to a V3 over V4. And then we know that the V4 over V3 is actually equal to 12. So V3 and V4, we just substitute 1 over 12. So we obtain that P4 is equal to 386.8 kilopascal. Scroll down. So now we have obtained all the value for the T, temperature and pressure for all stage. Now I need to calculate the W net. So we know that the W net is equal to Q in minus Q out, and then we know that the Q in is equal to 900 kilojoule per kilogram. So for the Q out, it's actually equal to a U1 minus U4. So we substitute the value of U1 and U4 into these equations, and then we obtain that the Q out is equal to 377.43 kilojoule per kilogram. So we sub this value inside the W net equations. W net is equal to 900 minus 377.43. So we obtain the W net is equal to 522.57 kilojoule per kilogram, in which the range is in between the 500 and 600s. And then after we find the network output, we will find the backward ratio. So the backward ratio is equal to work produced by a compressor equal to work produced by a turbine. So it means it's equal to a W in over W out, which is a U2 minus U1 over U4 minus U3. So we substitute the value inside and obtain the BWR is equal to 0.4238, which is 42.38%. And then for the efficiency, the formula is equal to a W net over Q in. So we substitute the value that we found just now, which is 522.57 kilojoule per kilogram over 900 Q in. So we obtain that the efficiency is equal to 0.5806, which is 58.06%. So at the right side is the temperature and pressure that I found at each stage. T1 is equal to 320 K, and then P1 is equal to 150 kilopascal, T2 is equal to 825.28 Kelvin, and P2 is equal to 4642.2 kilopascal, T3 is equal to 1826.95 Kelvin, P3 is equal to 10376.59 kilopascal, and T4 is equal to 816.64 Kelvin, and P4 is equal to 382.8 kilopascal. This is all the explanation of the calculation for the air standard assumption. Now I'm going to pass to my mate Jaya to explain about the cold air standard assumption part.
Thank you, Warning. So I'm going to explain on the cold air standard assumption where the value of K will be equals to 1.4. So as we know, we assume that the first P1 will be 150 kilopascal, T1 will be 47 degrees Celsius, which is equals to 320 Kelvin, and Q in will be 900 kilojoule, and the compression ratio will be 12. So first of all, we draw the graph. We draw the PV graph and the TS graph, and then at T1 equals to 320 Kelvin and P1 equals to 150 kilopascal, we know that the process from 1 to 2 is an isentropic process. So we can use the formula T2 over T1 equals to V1 over V2 power of K minus 1. So we just sub the value of T1 and then the value of K and times with the value of T1. So we get the T2 equals to 864.61 Kelvin. Same goes to the pressure. We will use the formula P2 over P1 equals to V1 over V2 power of K. So we just sub the value for P1 and the V1 over V2, which will be equals to the compression ratio value. So we get the value of P2 such 4863.46 kilopascal. Next, as we know, we already assumed the value of Q in equals to 900 kilojoule per kilogram. So we use the formula Q in equals to CV times with T3 minus T2. So from the table A2, we get the CV value as 0.718 kilojoule per kilogram Kelvin. This one for air. So after we sub, we get the value of T3, which was equals to 2118.1 Kelvin. So as we know, from point 2 to 3, the volume is constant. So we are going to use the ideal gas equation. So P2 V2 over T2 equals to P3 V3 over T3. So as we know, V2 is equals to V3. So we cut the V2 and V3. So we sub all the values and we get P3 equals to 11,914.38 kilopascal. So since the process 3 to 4 also isentropic, we are going to use the formula T over 4 over T over 3 equals to V over 3 divided by V over 4 power of K minus 1. Since we know that V1 over V2 equals to V4 over V3, which is equals to the compression ratio 12, so we are going to sub this value, just put 1 over 12 and then power of 1 minus 1.4 minus 1 times with T3. So we get the value of T4, 783.92 Kelvin. Same goes to pressure. We are going to use the formula P4 over P3 equals to V3 over V4 power of K. And then we sub all the values. We get pressure 4 equals to 367.47 kilopascal. So from this calculation, we obtain T1 equals to 320 Kelvin, P1 equals to 150 kilopascal. This one is the assumption. And then T2 equals to 864.61 Kelvin, P2 equals to 4,863.46 kilopascal, T3 equals to 2,118.1 Kelvin, P3 equals to 11,914.38 kilopascal, and then T4 equals to 783.92 Kelvin, and P4 equals to 367.47 kilopascal. So based on this information, we are going to calculate the W net. So we all W net equals to Q in minus Q out. Q in we already know it. So Q out is equals to CV times with T4 minus T1. So we get the value of 333.09 kilojoule per kilogram. So the value of W net is 566.91 kilojoule per kilogram is between the range given. And then we find the back work ratio. So back work ratio is equals to W in over W out, which is equals to compression work over turbine work. So this formula. So we cut the CV because same value, and then we get the value of back work ratio equals to 0.4082, means 40.82%. So next we are going to find the value of efficiency, which was equals to work net over Q in. So as we just sub the value 566.91 divided by 900, we get the value of 0.6299. So the efficiency will be 62.99%. So this is the calculation for coal air standard assumption. So next, I'm going to show the design of gas power cycle, Otto cycle. So first of all, for air standard assumption, as what Wan Ying calculated. So this is the value that we recorded from the calculation. So this is how the graph will look like for each calculation. Means the T1, this is T1, P1 value, this one P4, P2, and P3. Same goes to the TS diagram. So this is one T1, T4, T2, and T3. This one for air standard assumption. Next, this is the graph for coal air standard assumption. K equals to 1.4 as what I did calculated. So this is the value for P1, P2, P4, P3, and this is the for TS diagram. This is the value for T1, T4, T2, and T3. So now I'm going to pass the discussion to Muhammad Mohawiza. He will explain more on the discussion part. Thank you.
Okay, thank you, Jaya. And now I will explain more detail about both results in the discussions. So generally, the Otto cycle describes how heat engines convert gasoline into motion. This cycle is like other thermodynamic cycles, convert energy into thermal energy, which is then converted into motion. So the Otto cycle explains how gasoline-powered internal combustion engines, such as automobile, work. Otto cycle is used to convert gasoline into motion in the vast majority of automobiles seen on road today. So basically, the Otto cycle is a set of process used by spark ignition internal combustion engine, which is 2-strokes or 4-stroke cycles. Therefore, we know that the Otto cycle is an ideal thermodynamic cycle that powers spark ignition engines. In this assignment, we try to solve the Otto cycles problem by using two types of assumptions, which is air standard assumption and cold air standard assumption. So for cold air standard assumption, it is assumed that K is equal to 1.4 and the Otto cycle is not equal to 1.4, thus the solution must be done by using the ideal gas properties of air. So from the solution, the air standard assumption as a complex method in order to find all the needed values. Meanwhile, for cold air standard assumption, it shows simple steps to solve the problem. It is shown as for air standard assumption as we needed to use a lot of terms such as relative specific volume, which is BR, internal energy per unit mass, U, and interpolation. Meanwhile, cold air standard assumption doesn't need that terms and much simple step is needed. For both assumption, we assume that the Q in is equal to 900 kilojoule per kilogram. Compression ratio is 12, initial temperature which is 47 degrees Celsius, and initial pressure 150 kilopascal. And then we determine the temperature and pressure value for each point and calculate the value for work net, back work ratio, and the efficiency. So from the calculation that we made, work net in cold air standard assumption is 566.91 kilojoule per kilogram, which is more higher than air standard assumption, which is 522.57 kilojoule per kilogram. This is because the calculations show that the Q out value for the air standard assumption was 377.43 kilojoule per kilogram, while the cold air standard assumption was 333.09 kilojoule per kilogram. So when the Q out is increased, the work net will be decreased. That's why the work net for cold air standard assumption is more higher than air standard assumption. It shows even though the final output gives a different value, but still in the range of 500 to 600 kilojoule per kg, which is the objective for the assignment was achieved. Next, the performance of a power cycle is measured by its thermal efficiency. After we calculate the thermal efficiency for cold air standard assumption is 62.99%, which is higher than air standard assumption with the efficiency 58.06%. This is because in order to increase the efficiency of Otto cycle, it is depend heavily on the compression ratio of the cycle. So we see that increasing the compression ratio will increase the thermal efficiency. Other than that, another way to describe the performance cycle is the back work ratio. Basically, back work ratio is a ratio of compressor work to the turbine turbine work. As we calculate back work ratio for both assumption, we obtain 40.82% for cold air standard assumption, which is lower than air standard assumption with 42.38%. But the lower the back work ratio, the better the performance of the power cycles. So based on the calculations, it shows that because of the actual gains I used to simplify the analysis and keep it from deviating too much from the actual cycles. But to simplify the analysis to even easier, cold air standard assumptions are utilized. So we can conclude that Otto cycles continues to be an integral effective combustion cycles among many engines because it provides excellent efficiency and power output. That's all from us. Thank you.